Okay, so have you ever wondered how a figure skater can pull in their arms and suddenly spin at this just dizzying speed? Or, how a planet stays perfectly locked in its orbit? Well, the answer isn't magic, it's physics. So let's dive into the incredible and often totally invisible world of rotation.
We've all seen this, right? A graceful diver tucks into a tight ball to pull off multiple somersaults, or a skater goes from this slow, elegant spin into an absolute blur. So how in the world do they control their rotations so precisely, especially when there's nothing to push off of in midair?
Well, the secret is that for pretty much every rule you already know about moving in a straight line, things like mass, force, and momentum, there's a rotational twin that governs how things spin. It's kind of like a parallel universe of physics. So let's meet our first set of these twins. We all kind of get mass, right? It's just how much stuff an object is made of and how much it resists being pushed. Well, it turns out rotation has its own version of that. And it's called the moment of inertia, which we usually just write as the letter I. To put it simply, it's just an object's resistance to being spun. So if something has a high moment of inertia, it's really tough to get it spinning. And once it is spinning, it's really tough to stop. But here's where it gets really interesting. While mass is just about how much stuff you have, moment of inertia is all about where that stuff is located compared to the point you're spinning around. Okay, think about a simple rod or stick. If you try to spin it around its center, it's pretty easy. That's a low moment of inertia. But try to spin that exact same rod around one of its ends. It's way, way harder. The amount of mass hasn't changed at all, but where that mass is distributed has, and that completely changes the moment of inertia. All right, so if moments of inertia is kind of like rotational mass, then what's rotational force? I mean, if you want to make something move in a straight line, you apply a force. So if you want to make something spin, you apply a torque. Yep, torque is the rotational twin of force. It's that twisting action that makes an object change its spin. Think about tightening a bolt with a wrench. You're not just pushing on it, you're applying a twist. You're applying torque. Now, most of us probably remember this classic from high school physics, right? F equals ma. Force equals mass times acceleration. Super simple. The more force you apply, the faster an object's velocity changes. And here is its perfect rotational twin. Torque equals moment of inertia times angular acceleration. It means the same thing. The twist you apply is equal to the object's resistance to spinning multiplied by how quickly its spin speed changes. They're perfect mirror images. Okay, we've got rotational mass and we've got rotational force. Now we can finally put it all together and unlock the secret of that spinning skater. And the key, well, it lies in our final rotational twin. And that is angular momentum. It's the rotational twin of the regular momentum we're all used to. Just like linear momentum is mass times velocity, angular momentum is the moment of inertia times the angular velocity. Put simply, it's a measure of how much spin an object has. The formula for it looks like this. L equals I times omega. So that means the angular momentum, L, is just the product of the moment of inertia, I, its resistance to spin, and its angular velocity, omega, which is just a fancy way of saying how fast it's spinning. And this brings us to what is maybe the single most important rule in the entire world of spin, the law of conservation of angular momentum. What it says is that for any spinning object, as long as no external twist is applied to it, its total angular momentum must stay constant. It simply cannot change.
And this is the skater's big secret. When her arms are out, her mass is spread out far from her center, which gives her a high moment of inertia. So for her angular momentum to stay constant, her spin speed has to be low. But the second she pulls her arms in, her moment of inertia drops like a rock, and since her total angular momentum must stay the same, her spin speed has to skyrocket to make up the difference. See? It's not magic, it's just conservation.
And you see this principle absolutely everywhere. It's how a diver controls their somersaults. It's why a planet actually moves faster in its orbit when it gets closer to the sun. It's even why the Earth's rotation would slow down if it got hit by a bunch of meteorites, because that would increase its mass. I mean, this governs everything from the cosmic to the subatomic. It's incredible. So let's just zoom out and bring this all together. We've been talking about these concepts as twins, living in these parallel worlds. But the final takeaway, I think, is even cooler than that. They aren't really separate worlds at all. They're two sides of the same coin, two expressions of the exact same fundamental laws of physics that describe every single kind of motion in our universe. And look at this. You can see the entire idea in one place. On the left, everything you know about straight line motion. On the right, it's rotational twin. Velocity has angular velocity. Mass has moment of inertia. Force has torque. And linear momentum has angular momentum. It's just this beautiful, perfect symmetry. In fact, out here in the real world, these two things are combined all the time. I mean, a rolling ball isn't just moving forward, it's also spinning. It has both linear energy and rotational energy at the same time. They're just two parts of the same story of motion. So, the next time you see a spinning top or a turning wheel, or even just the swirl of cream in your coffee, you'll know the secret. It's a whole universe of twists, inertia, and conserved momentum. Now that you know the physics of spin, what other spinning objects do you see differently?